Hi. So I wasn't able to find a really good lesson or video online that was already made for the difference quotient. So I thought I'd just make one. And I know I've shown or I found a couple that show stuff about the average rate of change. But for right now, let's go back and just make sure we cover or review a little bit of that, just so it helps solidify what the difference quotient is. So here's my function where I have f of x equals 9x minus 4. And I want to find the average rate of change when starting from x1 of 3 to x2 of 6. What is going to be the average rate of change in this function? Well, here's what we're going to do. Let's remind ourselves that the average rate of anything, just like speed is always a change in some output. So if we were talking about speed, for example, the output would be a change in distance all over the change in time. How long did it take us to get there? And it wouldn't matter necessarily if we went to the grocery store and then back down to the south, depending on where you might be, I don't know. Or if I went from Bangor to Hamden up to Old Town, the average rate of change would be just the change of distance from my starting point to my end point and how long it took. Now here in this function, it doesn't matter if this is a parabola. In this case here, it happens to be a straight line that looks a little bit like probably something like this, give or take. I'm over exaggerating. It's rough. Where this is going to be x1 and this is x2. Okay, so in order to find our average rate of change, it's going to be the function at 1. So what is the function? We need to figure out what is f of x when f of x is, or an x is equal to 3. So I want to plug 3 in for x here, and I get 3 minus 4, which is the same thing as 27 minus 4, or 23. So we know that this is going to be 323. Now what is the function's value at x equals 6? 9 times 6 minus 4, 54 minus 4, or plain old 50. So we know that this value here is now 650. So the average rate of change is the change in my function values all over the changes in x. Well, I went from the changes in my function values is the up and down, or what we call the y here. So we went from, ended up at 50, but we started at 23, and that corresponds with the x values, side to side, with an input of 6 and an input of 3. It's 27 all over 3, or 9. In this case, the average rate of change for this function is 9. Now notice, for linear functions, this is the slope. But this is only true for linear functions. That's important to remember. Now, let's take and see how this is related to the difference quotient. So, here's the difference quotient. All right, so if you look up the difference quotient, you will find out that the difference quotient is this really crazy function looking thing, and at first it might be a little intimidating. And this is the simplified version. What is all of this thing saying here? Well, this is saying the function of a value of x plus h, whatever that value might be, and you're going to subtract original f of x, its starting point, where it ended and where it started, divided by the change between those two x values. So let's apply that to the original function I had just a moment ago. Let's take a look at that. What does that mean? Let's see. Where did I put that? Is it on the back side here? Sorry, I lost my notes for a second. There it is. Okay, so my f of x is, remind ourselves, x minus 4. What would f of x plus h be? Now we're working with letters and not numbers. Well, if this was a number, Just because now I've added letters doesn't mean the rules have changed. If this was a number, I would just simply replace that for x. So I'm going to do the same thing here. Just replacing what's inside the parentheses for what was just x all by itself. All right, so this is the two pieces. This one is going to get shoved up in here, and this one will go over here. And right now, h is my difference. So let's put that in here. Let's see what happens. All right, so we have 9x plus h minus 4. And I want to put a grouping parentheses around all this stuff so we don't lose track of what's what. And divide it all by our change between this spot and this spot right here, which is just going to be h. I'm going to distribute the 9. So we get 9x plus 9h, and then minus 4. And then I'm going to distribute this negative sign through. Don't forget that. It goes to both places. Common mistakes for most folks. Oh. Now I'm going to take and I'm going to simplify by eliminating anything that's the same throughout. So here's a 9x minus 9x. So they're just going to go away. And then there's a negative 4 and a positive 4. So that's going to go away. And the only thing I'm left with is 9h over h. The h's cancel. And so my difference quotient for this function is 9. Just like the average rate of change. Just like the slope. This only is true for linear functions. The real power for a difference quotient is when we deal with non-linear equations. And so here is the deal. Let's say I have some function that's dependent on time here, 10t squared. All right, let's find the difference quotient for this thing. What is that going to happen? What's going to happen there? Well, to start off with, just like before, I'm going to substitute everything that was t for t plus h. And then all of a sudden, things already start to look a little bit different. So I want to expand this thing here. And if I'm showing all my steps and you guys are finding it tedious, I'm sorry. I just like to show them all because one of the things I dislike in lots of math books is those magic steps. Well, you clearly can see from this here, the answer should be, but if we all could see that, we wouldn't need the book. So now here, I'm going to FOIL these out. 10. First, 2t squared. Outers, t times h. And inner, t times h. And last, h squared. Combine like terms and distribute the 10. So you get 10t squared plus 20th plus 10h squared. So I added these two here and multiplied by 10. So 2th times 10 is 20. Okay, so this is the first part that I'm going to plug into my difference quotient. So let's see here. So remember, the difference quotient is going to be t plus h minus dt of t rather. Oh, come on. Let's get the eraser. There we go. There. That's better. All over h. Well, I just calculated my d of t plus h. It's right here. So I'm going to replace this here. 10t squared plus 20th plus h squared minus the original 10t squared all over h. Cancel out all the terms that are opposite right here, this one and this one. 20th plus h squared all over h. Cancel out all the h's that are common. And so my difference quotient for this function is right here. Now this is a little bit different than what we've seen before. We still have variables involved. Well, what good is that? What does this really tell us? It's not quite as straightforward as our traditional average rate of change, because the average rate of change, we put in 2 points that we knew both of things about. The difference quotient becomes very powerful when it comes to nonlinear functions, and if we only know 1 point. See, now I can take this difference quotient, which was 20t plus 10h. And if I say it was about speed, let's see, I want to know the speed of a car at 5 seconds, t equals 5 seconds, and I want to know how it changed within 0.05 seconds away. How fast is this car changing? I don't know anything else about this endpoint besides of how far away it is from the original point. So here I can just put it in here, times 5 plus 10/05, and we get 100 plus 0.5 rather. Oops, got carried away with the zeros again. All right. And we would find out that after 0.05 seconds, the speed of this car might be 100.5 meters per second or miles per hour. This is just an arbitrary example. Instead of knowing, actually being able to know or having to know what that endpoint is, what this value is, in order to calculate this average rate of change, I now have a function, a difference quotient, that tells me how the function changes in relation to the starting point where I might be in that function and how far away I'm looking. So these things will change very dramatically depending on what's going on. So to highlight that, let's say I wanted to know how far, what the difference quotient or what the value would be if I wanted to know if the original time was 5 seconds, but what would it be like with an h of 5 seconds away? And so I can just plug this in. So this is now 100 plus 50 equals 150. And this would change dramatically if this was a 4 seconds, the starting point, or the 0, what have you. Remember, because of the original equation, d of t was exponential. This thing is going to change exponentially very quickly as time goes on. So the difference quotient, again, allows us to predict how these changes might happen, knowing only a specific starting point along this graph and how far away we want to look. I hope that helps. If I run into any other problems, or if you guys have requests for a specific topic as you're going through these, please feel free to contact me.